Good day, I am Charles Godric Lacerna, together with
I am Russel Dalisay,
and we are ready to explore the world of differential equations here at GETV.
Welcome. Have you ever wondered how scientists predict the weather? How engineers design bridges, or how doctors model the spread of diseases?
These might seem like totally different fields, but they all rely on a powerful tool in mathematics and differential equations.
And in this video, we'll explore what differential equations are, where they show up in our lives, and why they're so important.
Let's break it down. A differential equation is a type of mathematical equation that links to a function to its derivative. It's basically the world of change.
Exactly. These equations help us to understand changes of things over time, or space, from how temperature changes during the day, or how population grows, or sinks over generation.
They help us model everything from simple processes like cooling coffee to more complex systems like the motion of planets or the process of diseases.
Now that we know what differential equations are, let's look at where they show up in the real world. In physics, differential equations help us to understand how objects move and interact with each other, whether it's the orbit of planets or the behavior of tiny particles.
Differential equations are everywhere. They play a critical role in so many areas that shapes our daily lives. Let's dive into some of the most important fields.
Differential equations are widely used in real-life application, especially in the field of physics. Differential equations, especially those derived from Newton's second law of motion, play an important role in modeling and understanding the forces and motions that shapes everyday experiences, from designing safer vehicles and predicting natural phenomena to optimizing industrial processes. They provide a powerful mathematical framework for solving real-life problems and derive technological advancement.
One of those equations is the Newton's second law of motion, also known as the force equals mass times the acceleration. It is expressed as a second-order differential equation that describes how the motion of an object changes due to applied forces.
Real-life application of Newton's second law of motion is the acceleration and deceleration of an elevator. When you enter an elevator, you feel the forces as it starts and stops moving. Engineers calculate these forces using Newton's second law to ensure that the elevator accelerates and decelerates smoothly without causing discomfort and exceeding safety limits.
Now, physics is all about understanding the forces of nature. But what about engineering? How do we use math to build things like bridges and skyscrapers? Engineers rely on heavily differential equations. They use them to predict how structures will behave under stress, whether it's a bridge with heavy traffic or a building during an earthquake.
Exact. Equations help us to understand things like how materials were done over time or how a machine operates. They make sure that everything we build is safe, reliable, and efficient. Let's see how differential equations play in a major role of engineering.
In geodetic engineering, differential equations model the Earth's surface, accounting for terrain variations and gravity, which is essential for precise calculations of distances, elevations, and angles. This accuracy is crucial in mapping, surveying, and satellite positioning. Similarly, in road designs, these equations analyze the stresses on each layer over time, ensuring surfaces can endure heavy loads and harsh weather. Factors like temperature, fluctuations, and moisture are considered to guarantee long-lasting design. The same principle applies to building, pipelines, and tunnels. It's fascinating how math influences our world. Each equation contributes to safer, stronger designs, allowing us to predict stability and reliability with confidence. Every detail matters, making our work vital for the safety and longevity of infrastructure.
We'll be back after a short break.
In this short break, we're going to discuss the exact differential equation. Exact differential equation have two formulas. The first one is the integral of m of x and y dx plus the integral of n of y dy equals 0, wherein the y is the constant. The other formula is m of x, integral of m of x dx plus the integral of n of x and y dy equals 0, wherein the x is the constant. To understand deeper those formulas, we have here the example of exact differential equation. So 2xy squared minus 4dx plus 2x squared y plus 3 dy equals 0. So in this equation, 2xy squared minus 4 is the m and 2x minus y plus 3 dy is the n. The first step that we're going to apply here is to test the exactness of the equation m and equation n so that we can know if this is solvable using the exact differential equation formulas. Partial derivative of m and partial derivative of y, wherein we're going to differentiate in terms of y and we will consider the x as a constant. On the other hand, partial derivative of n and partial derivative of x, wherein we're going to differentiate in terms of x and we will consider the y as a constant. So in partial derivative of m, the derivative of 2y squared is 4y and we're just going to write the x since it is constant. The derivative of 4 is 0, while in partial derivative of n, the derivative of 2x squared is 4x, and we will just also going to write the y since it is constant. So the derivative of 3 is equal to 0. So as we can see, the partial derivative of m and partial derivative of n is equal to each other, meaning to say that the given equation is an exact differential equation. So the next step that we will going to do is the application of the formula. So in this equation, we will going to use the formula integral of m of x and y dx plus integral of n of y dy equals 0, wherein the y is the constant. But you can use any of those formula naman because it will just give the same answer. So in this part, we're going to apply the equation to the formula. So y will be the constant and we will write the value of m, which is 2xy squared minus 4 dx plus the n, which is 2x squared y plus 3 dy equals 0. So the integral of 2x will be 2 times x squared, then we're going to write the y since it is constant over 2 minus the integral of 4, which is 4x, plus we're going to cancel the 2x squared y since there is no given constant here, and the derivative of, or the integral of 3 is 3y equals 0, and we will simplify it and this will become x squared plus y squared minus 4x plus 3y equals 0, plus c equals 0, and this will become our final answer. So that would be all. Back to you guys.
But let's move on from the world of structures to living systems. Differential equations are also crucial in biology, where they help us understand how organisms grow and how diseases spread.
In biology, differential equations are used to model the growth of populations, the spread of disease, and even how cells divide.
For example, during a virus outbreak, scientists use differential equations to predict how fast a virus will spread and how to respond to control it.
They give us the tools to understand complex biological processes and make informed decisions, especially in public health.
In biology, differential equations are crucial for analyzing and predicting the behavior of complex biological systems. They enhance our understanding of processes such as population dynamics and cell signaling. In population dynamics, differential equation model changes in population size over time. For example, the logistic growth model describes initial exponential growth followed by a slowdown as resources become limited, expressed as the derivative of x with respect to t is equal to rx times the quantity of 1 minus x over k, where x is the population size, r is the growth rate, and k is the carrying capacity. Overall, differential equations are vital for modeling biological processes. As computational method improves, their application in biology will continue to expand, enhancing our understanding of living systems and informing medical research.
Now, from biology to economics, differential equations are also key in understanding how economics grow, fluctuate, and interact.
In economics, this equation helps model how markets behave, how inflation changes, or how investment grow over time.
They allow economists to predict trends and understand how different factors like government policies or global events can affect financial markets.
By using these equations, businesses and governments can make better decisions based on real predictions, not just guesses.
Differential equation plays a vital role in shaping our lives by enabling economists to model and analyze complex economic phenomena. The social model, for instance, uses the differential equation dy over dt equals sy to the power of alpha times 1 minus y divided by k. To explain long-term economic growth, where y represents GDP is the saving rate, A is the output elasticity, and K is the capital stock. This model helps policymakers understand the impact of investments in human capital and technology on economic. Economists employ differential equation to analyze inflation and employment rates of assets in the Philips score. dy over dt equals beta times the difference between u and u asterisk, where pi represents inflation, u is in employment, u asterisk is the natural rate of employment, and beta is a parameter. This model enables policymakers to anticipate and mitigate economic shocks, making informed decisions on monetary and fiscal policies. Differential equations also underlie financial modeling, such as the Black-Scholes model for option pricing. The partial derivative of v with respect to time, t plus r times s times the partial derivative of v with respect to s plus 1/2 sigma squared s squared times the second partial derivative of v with respect to s equals r times v, where v represents the option value, s is the stock price, r is the risk-free rate, sigma is the volatility, and t is the time. This model helps investors and businesses manage risks and make informed investment decisions, ultimately shaping our economic lives.
As we can see, differential equations don't just appear in textbooks. They are crucial in so many aspects of our world. So there you have it. Differential equations are just the language of change, connecting us to the system and forces that shapes our lives.
Next time, you're faced with a math problem involving derivatives, remember, you are learning the math that's derived the future.
Learning the math that drives the future.
You're learning the math that drives the future.
You're learning the math that drives the future.
You're learning the math that drives the future.